Everyone can hear me fine? Yeah? Okay, great. Thanks for coming. So the title of my talk is Learning Across and Within Instances for Mechanism Design. And the material I'll cover is joint work with my advisors, Nina Balcan and Thomas Sandholm. So mechanism design is a vastly studied field in economics, but the design of optimal mechanisms is often a very difficult problem. So in the classical mechanism design approach in 1981, Meyerson in the seminal result showed how to sell a single item in a revenue maximizing way. But today we still don't know how to sell two items optimally. So in 2003, Conitzer and Sandholm introduced this paradigm of automated mechanism design, which basically says, don't worry about explicitly getting closed form analytic characterizations for these difficult problems. Instead, maybe you can just write like a program or an optimization problem that you can feed the details of the mechanism design setting into, and then that'll spit out a high revenue auction or a good mechanism. But they show that in many settings, this kind of approach runs into computational intractability due to requiring details of things like value distributions. So more recently, there's been this exciting line of work on using machine learning to automatically design auctions and mechanisms and pricing schemes. So here, it takes a more arguably realistic approach where you don't need to know details about distributions from which buyers are coming. You just assume you have sample access, and then can you unleash a learning algorithm to nevertheless learn maybe not exactly optimal, but a nearly optimal mechanism in this setting. And there's been a very recent and very exciting long line of work. And in this talk, I'm going to discuss some new ideas that stem from this idea of sample-based automated mechanism design. In the first part, I'm going to talk about a specific instance of learning mechanisms from samples. I'll talk about some more algorithmic challenges of efficiently learning a specific pricing scheme. And in the second part, I'm going to talk about a slightly different setting where there's actually just a fixed population of buyers. You don't have samples. And in this setting, I'll talk about two different problems the seller might face. And I'll come back to the details of that second part when I get there. Okay, so in the first part, I'm going to talk about efficiently learning high revenue two-part tariffs from samples. A two-part tariff is a pricing scheme that consists of a single upfront lump sum fee, which I'll denote by P1, and a per unit fee, P2. Various goods and services are priced using a two-part tariff. For example, Keurig sells coffee machines, the upfront fee, that require proprietary coffee pods, the per unit fee. Gym memberships is another example. They often require fixed membership fee as well as a monthly fee. So in the most basic setting, the seller has K units of an item to sell to a single buyer. The buyer has a valuation function V, which specifies how much she values each possible discrete quantity of units. When faced with a two-part tariff, P1, P2, a buyer with valuation function V is going to choose to purchase a quantity Q to maximize utility, which is just V of Q minus the price paid. As long as that utility is greater than 0 for some quantity. If the buyer purchases Q units, then the seller's revenue is just the payment made by the buyer, which is P1 plus Q times P2. Now, of course, the main challenge here is that the seller doesn't actually know the buyer's valuation function. Instead, we assume that the buyer's valuation is drawn from an unknown distribution, and the seller has access to samples from that distribution. And the seller's goal is to use those samples to efficiently design a two-part tariff that yields nearly optimal expected revenue on a new unseen buyer. So the standard way to do this is to maximize the empirical revenue over the samples. So previous work by Balcan, Sandholm, and Bittersick shows that log K samples suffice to guarantee with high probability that the empirical revenue maximizing two-part tariff is nearly optimal on a new buyer, where K, recall, is the total quantity of the item. And again, here nearly optimal means with respect to the two-part tariff that maximizes expected revenue. And this is something that the seller can't compute explicitly himself, since the underlying valuation distribution is unknown. So our first main result is an algorithm with runtime that is cubic in the number of samples n and the total quantity k that that computes the empirical revenue maximizing two-part tariff. So recall here that we're in the single buyer setting. So each sample consists of only one buyer, and I'll later quickly go over how to generalize everything to the multiple buyer setting. So the space of two-part tariffs is infinite, but there's two insights that allow us to reduce the search space to a set of n squared times k squared two-part tariffs. The first observation is that if P1, P2 is a two-part tariff that maximizes empirical revenue, the two-part tariff line that has y-intercept P1 and slope P2 must pass through a point of the form Q VI of Q for some quantity Q and some sample I. And here VI of Q is the valuation function of the single buyer in sample I. This can be seen through the presented diagram. So consider a buyer whose valuation function is displayed by these open dots. That buyer is going to purchase the same quantity when presented with either one of the two displayed lines, because they're vertical shifts of one another. Hence, the one that is higher up will generate more revenue. So you would never consider a two-part tariff line that does not pass through one of these points. Okay, so now that we only need to consider two-part tariffs that are sort of hinged at such points, the second observation is that there's only a finite set of slopes to consider for each such hinge point. And this can also be visualized as follows. So consider hinging a two-part tariff line at such a point and consider continuously rotating it. Each buyer's utility maximizing quantity can then change at most k times, and revenue is going to be a linear function of P1 and P2 between two consecutive changes. So it's straightforward to compute these change points, so these slopes, and thus for each of the n times k hinge points, there are at most n times k change points, giving a total of n squared times k squared tariffs to search over. And computing the empirical revenue for each of these tariffs takes n times k steps. So the overall complexity is n cubed times k cubed. And in practice, this algorithm was dramatically faster than solving an integer program formulation of this problem with Gurobi, which was the only sort of existing algorithm or even suggested way of computing two-part tariffs. Yeah, so like averaged over 10 runs on randomly generated instances with 5 units of an item and 600 samples, our algorithm found the optimal solution in less than 23 minutes, while Gurobi took over 3.5 hours. So one way for the seller to generate significantly more revenue is to offer a menu of two-part tariffs, which is just a list of L two-part tariffs. When faced with a menu of two-part tariffs, a buyer now can choose to purchase some quantity Q of tariff R in order to maximize utility. So the buyer now has these 2 degrees of freedom in choosing how to purchase. Menus of two-part tariffs are also prevalent in real life. For example, wholesale stores like Costco, amusement parks, these all frequently offer various tiers of membership, which usually consists of lower future payments for larger upfront payment. So we give an algorithm that finds the empirical revenue maximizing menu of two-part tariffs with runtime that's exponential only in the menu length, but polynomial in all the other parameters. And just note that in most applications, the menu length L ought to be a small constant like 2 or 3, just so that humans can read, can parse and understand the list of options being presented to them. So our algorithm exploits geometric properties of the space of two-part tariff menus, R to the 2L. In particular, they're n times KL squared hyperplanes that partition the space of menus such that empirical revenue is a linear function of menu when restricted to each region determined by these hyperplanes. So what are these hyperplanes? Basically, for each sample I, for each possible pair of quantities Q and Q prime between 1 and K, and each pair of tariff indices R and R prime, we're going to write down this hyperplane that represents the decision boundary that consists of menus for which a buyer with valuation function VI is indifferent between purchasing Q units priced by tariff index R, is indifferent between purchasing according to that and purchasing Q prime units of tariff R prime. So you put down these hyperplanes for every possible pair of quantities and indices. Then inside a single region, which is the intersection of all these of half spaces determined by all these hyperplanes, the quantity and tariff chosen by each buyer is fixed. So the empirical revenue is linear as the menu varies in a given region. So then everything else is pretty standard. These hyperplanes can partition the space into at most so many convex polytopes. Over each polytope, the optimal menu can be found by just solving a linear program that has a polynomial number of variables and constraints. And furthermore, a representation of each region as a set of LP constraints can be computed in well, polynomial time other than the menu length. So then we solve such an LP in each region, and so the optimal menu can be found in n times k to the O of L time. So far, everything I've talked about has been in the single buyer setting. So each sample consists of only one buyer. But everything I've talked about easily generalizes to the setting where the seller has k units to sell among n buyers. And in this case, each of the samples just consists of n buyers, and both algorithms just work. There's nothing really you have to change other than checking that that everything is feasible and only those k units get sold. So in the multiple buyer setting, another way for the seller to increase revenue is via market segmentation. Here, each buyer comes with an attribute like age or geographic location that's going to determine membership in one of M markets. So the seller now can set M different two-part tariff menus where buyers in market I are presented with menu I and can only purchase according to menu I. So the seller first needs to make sure that the set of menus offered to each market has to be feasible. So the sum of the demands of the markets in each sample should not exceed k, and particularly in the unseen sample, it should generalize well and should still be feasible. So we should show that any solution that is feasible for each sample in a large enough sample set is with high probability going to be feasible for any future unseen sample of buyers. But it turns out that market segmentation, even in very simple cases, induces computational intractability. So even if you assume buyers have additive valuations, and in this case, it turns out that the parameters of the menu length and even the quantity k actually vanish from the problem. So it turns out that every buyer is going to want to buy the entire bundle of item or the entire k units of the item, and the problem reduces for the seller to just choose single prices for each market. But even in this case, finding the empirically optimal collection of market prices is NP hard. But not all hope is lost here, because if you assume that across markets, each buyer looks the same, and this is maybe a realistic assumption, you know, if it's something like a gym membership, then maybe if markets are just different regions or different cities, you don't assume that people value things too differently. Then as long as each buyer across each market is independently drawn from the same distribution, then you can sort of forget the market segmentation, compute the optimal non-market segmented solution using one of the algorithms that I discussed, and then just reuse that solution in each market. So this is not going to compute the empirically optimal solution, which is still NP hard, but this is going to result in a solution that is nonetheless nearly as good as the optimal solution with high probability. So in this case, we can pretty much circumvent this computational hardness and use either one of the algorithms that I had presented for either for finding a single two-part tariff or finding a menu of two-part tariffs. Okay, so now I'm going to move on to the second part of the talk. And this next part of the talk is about designing auctions when there's only a single instance of a population of buyers. So before getting to the specific topics, I'm going to try to give a quick crash course on combinatorial auctions in a few slides. So in a combinatorial auction, Seller has m indivisible items to sell among a set S of n bidders, and bidders have combinatorial valuations. So they can express how much they value each distinct bundle of the items. Now, for reported valuation functions of the n bidders, an auction M is specified by an allocation function and payment functions. So the allocation takes in the reported valuations and says who gets each item, and the payment just says how much each bidder has to pay. And what we impose on all these auctions is that they ought to be truthful or incentive compatible. So that means that if your true valuation function is given by VI, your utility from truthfully reporting your valuation function as being VI to the auction should at least be weakly better than lying and saying that your valuation function is VI hat, which is what this condition says down here. So the canonical example of a truthful combinatorial auction is the so-called Vickrey-Clark-Groves or VCG auction. So the VCG auction chooses the allocation alpha star that maximizes welfare. And welfare here is just the sum of everyone's value for what bundle they get. And the payment collected from bidder I is given by this formula here, which basically represents how much bidder I harms the welfare of everybody else by participating in the auction. So in this payment term, this term on the left side is the maximum welfare everybody else could enjoy if bidder I was absent from the auction. And the term on the right is the welfare that everybody actually gets to enjoy due to bidder I being in the auction. So a more simple instantiation of VCG that maybe more people might be familiar with is the second price auction. So in the second price auction, the highest bidder gets the item and pays the value of the second highest. Second price auction for selling a single item goes to the highest bidder and she pays the value of the second highest bidder. And VCG is known to be a truthful auction. So now I'm just gonna quickly go over a parameterized class of auctions that generalizes VCG. The details of this are not super important, but it's mainly to illustrate that there exists large, rich classes of auctions that can be parameterized in sort of complicated ways that generalize the VCG and can be used to find like high revenue auctions. There are many cases where VCG can do very poorly in terms of revenue, but there are huge auction classes that, you know, if we want to do some sort of machine learning over auctions, there are huge auction classes that we can search over. So just for the sake of this talk, the one I'll present is, these are called lambda auctions. And these are parameterized by vectors of boosts that specify boosts for every possible allocation of the items. And how a lambda auction is going to work is it's going to work in the exact same way as VCG does, except with this sort of modified welfare function. So it's just going to compute the allocation alpha star that maximizes the total welfare plus the boost assigned to that allocation. And the payment collected from bidder I is going to be, you know, what you would expect. So similar to VCG, but with this modified welfare that includes these boost terms. And individual lambda auctions are all known to be incentive compatible. And I should say lambda auction is just one example. There are many other parameterized generalizations of the VCG auction. Okay, and the last thing I'll say before going into the actual new topics are, we'll compare all of our revenue guarantees to this very strong benchmark of W of S, which is the welfare of the welfare maximizing allocation. And this is a very strong benchmark because no auction can ever obtain revenue that is more than this quantity, just because no bidder would ever pay more than her value for the bundle she receives. Okay, so now I'm going to talk about learning within an instance. And okay, yeah. So I briefly talked mentioned in the very beginning of the talk that there's been this recent flourishing line of work about learning high revenue auctions for limited supply from samples. So in a sense, you can think of it as being learning across instances. But what if the mechanism designer doesn't even have access to samples? So there's a set S of bidders that shows up. How should the mechanism designer, or how can the mechanism designer design an auction that performs well on S with absolutely no prior information about S at all? So there's no assumption that bidders come from a distribution, anything like that. So in the unlimited supply setting, when there's an unlimited supply of each item, Balcan, Blum, Hartline, Mansour give an answer to this, or make progress towards answering this question in a FOCS 2005 paper. And they propose the so-called random sampling mechanism, which I'll talk about in just a second. And it can be viewed as doing some sort of learning within an instance. So even when you don't have any prior information about the bidders, it's still possible to do some sort of learning. And this is the only work I'll talk about random sampling, but there have been several follow-up works on really analyzing and proving strong bounds on the performance of such random sampling mechanisms for unlimited supply. Okay, so what is a random sampling mechanism? It's very simple to describe. So there's this pool S or set S of bidders. You flip a coin independently for each bidder and partition them into two sets based on whether the coin is heads or tails. For group S1, you compute the optimal mechanism for S1, call that M1. For group S2, you compute the optimal mechanism for S2, call it M2. And then you just do this crisscrossing thing. You run the auction M1 on group S2 and vice versa. And the reason for this sort of crisscrossing is that it ensures truthfulness or incentive compatibility. Because if I'm a bidder in group S1, what I say does not influence the design of the auction that I get to participate in. So there's nothing I could say that could influence the design of the auction that I get to actually participate in. So as long as the class of auctions that I'm optimizing over, as long as that class contains truthful auctions on its own, then this whole process is going to be truthful. Right. So in this FOCS 05 paper, the authors show that this random sampling mechanism satisfies a sample complexity like guarantee. So as the number of bidders grows large, the random sampling mechanism approaches a 1 minus epsilon approximation to the optimal welfare of any mechanism in M. But the analysis of this random sampling mechanism crucially relies on lack of supply constraints for each item. So let me now discuss some difficulties of limited supply. The main difficulty is that allocations of items must be feasible, since there's only one of each item. In Balcan, Blum, Hartline, and Mansour's analysis of the random sampling, they look at so-called item pricing mechanisms. So they set optimal prices for each item and then do this crisscross crossing, and they let buyers purchase according to their demand functions, which just means you show the buyers these prices for all the items and then let buyers come and say, okay, this is the bundle of items that I want. And you don't have to worry about like the order of the buyers or anything like that, since there's an unlimited supply. It turns out that directly adapting this to limited supply is like fairly tricky. There have been some attempts, but all of them sort of require complicated benchmarks on what you can do. Like maybe you need to consider a random permutation of buyers arriving in that order, because when there's limited supply, it's not so easy to just say, okay, everyone go purchase according to your demand function. So first of all, to solve that, we think about these variants of the BCG auction that prescribe feasible allocations beforehand. So we don't give buyers really the power to choose according to their demand functions. We prescribe feasible allocations beforehand, and the way that those allocations are prescribed is done in an incentive compatible way. Here's another thing that illustrates like, okay, so we want to try to adapt random sampling to work for limited supply, but some obvious attempts maybe don't work so well. So here's one attempt. We'll partition S into two groups as before. We'll compute the optimal mechanism for group S1 and then run it on S2. So we won't crisscross, we'll just sell to people in S2 to maybe this will solve our issue with feasibility and feasibility. So here's an example, a simple example showing how this can do very poorly. So just consider the sale of a single item. sold via second price auction with the reserve price. So just to refresh, a second price auction with the reserve price R, it sells the item to the highest bidder, and the payment collected from that bidder is going to be the maximum of the reserve price and the second highest bid for the item. So in this case, suppose here I've shown there's one bidder with a really large value. And it doesn't even have to be really large. It's just the bidder with the largest value for the item. With probably 1/2 is going to be in sort of this in this learning group that we use to determine the auction. The revenue optimal reserve price is to just set a reserve price equal to his or her value. And because in S1, if we were able to do that, we would extract the entire value as revenue. But then applying that to group S2 is going to get a revenue of 0, since nobody in S2 values the item as high as that bidder. So with probably 1/2, this attempt gets 0 revenue always in this single item setting.
So Siddharth, if you were happy with a factor 2, you'd be okay with this one, right? You want 1 minus epsilon or something.
Sure. Well, it's not even that we want 1 minus epsilon. It's just like I want something that's. So I mean, this might be fine, like in factor 2. But for example, like if I was, this is just in the single item case. So if I was selling multiple items, then potentially much worse things can happen. So like we have some examples also in the paper that show like, okay, in the multiple item setting, then like things can be even worse.
Oh, okay.
So yeah, right.
Fair enough. Thanks.
Yeah, so the things I present are not necessarily even going to be as good as factor 2 approximations, but this is just to illustrate that like this obvious modification of random sampling can like do poorly. Oh, also actually, here's a better answer to the question that just came into my mind. Yeah, this is a factor 2 approximation in expectation, but I want actually to be able to say with high probability it's going to get this revenue guarantee.
Okay.
So things like with probability 1/2 is if some really bad case happens, I'm not happy with that. So I want to say with really high probability, the revenue is pretty good.
Good.
Yeah. Okay. So maybe another attempt to modifying random sampling is, okay, maybe 2 groups wasn't enough. So like what I guess I like to think about the failure of the previous example as being sort of, if the auction class is rich enough, you can really overfit to like a small number of bidders in the group that you're doing learning over. So another attempt is maybe, okay, partition this into n+1 groups, use the first n groups for learning, and then run what you've learned on the last group. And then like the issue like before maybe wouldn't happen, because if you're trying to like maximize empirical revenue, then just because there's one large bidder in one group, he's not going to affect everything. But this is also kind of problematic because n might need to be pretty large for like generalization guarantees to hold. And if you're doing a partition of S, then each of these groups would contain a really tiny fraction of bidders. And just by doing that, you've already lost a ton of revenue. Okay, so to sort of circumvent all these issues, we present this learning within an instance mechanism. And how this works is it's first going to sample a participatory group of bidders. And this is going to be some random p fraction of bidders, including everyone independently with probability p. Then we set those bidders aside. Then from the remaining pool of bidders, we're going to sample several learning groups. So each learning group is just sampled by including each bidder independently with probability q. And I should just say that these learning groups are not like a partition or anything. So once we sample one learning group, the next learning group we sample from the entire pool of bidders again, excluding S par. So these learning groups can have overlap, that's fine. Then we compute the empirical revenue maximizing mechanism over the learning groups, and then we run that mechanism on S par. So that's going to be the mechanism we analyze. And I should note that is, if M is a class of incentive compatible mechanisms, then this mechanism is also incentive compatible for the same reason as in random sampling. So if you're a bidder in S par, then what you report does not affect the design of the auction that gets applied to you. And if you're not in S par, then you are not getting any items anyway. So what you say does not really matter. So you have no incentive to lie. So here's the structure of the basic general guarantee that this approach satisfies. And
Siddharth, hey,
yeah.
one more question.
Yeah.
So we're trying to maximize revenue. What kind of constraints do we have? Like, do we have like a single item, multiple items?
Oh, no. So yeah, so this is multiple items, M items, and bidders have combinatorial like values. So they have, and oh, maybe you're asking about like restrictions of the valuation functions. I'm not actually,
I mean,
yeah.
Yeah, no, so I was just, so there are M items, each bidder can get as many items as they want. And so they have a general set valued function, whatever.
Yeah.
Okay.
But there's only one of each item. That is the crucial thing. So it's a limited supply. So there's one of each item, M items, and
okay, cool.
Yeah. And yeah, and so far, and we're actually not making any assumptions on valuation functions, which also kind of differentiates this from a lot of past work on this problem. So, okay, this is the basic general guarantee. And so far, I'm just going to go through the terms here. So far, it's not really saying anything interesting, but this is just a basic form, and we'll go into making it more meaningful. So here, N sub M is a standard sample complexity term that arises from like these generalization guarantees from learning theory. So it's saying how many samples does the mechanism designer need to draw, like how many learning groups does he need to draw? As long as he draws this many, then the revenue obtained on the participatory group is at least, and remember, WFS here is like the maximum welfare possible on all the bidders. So we're just comparing it to this benchmark. This here is just the loss term. So L here, again, is not saying anything interesting yet. It's just how much is lost from restricting to this P fraction minus epsilon. This epsilon term just arises from the error in learning. And then minus this additive loss term, which is a complexity / uniformity measure that we call partition discrepancy. And partition discrepancy basically measures the error that we incur due to applying the mechanism on this new group of bidders that we haven't used for learning at all. So it's the maximum discrepancy that any mechanism in M suffers between the revenue on the participatory set of bidders versus the expected revenue of M on a randomly chosen learning group from the other pool of bidders. Okay, so there's two things we do to make this guarantee more concrete. The first is a bound for partition discrepancy in a special case. So when P is 1/2, so we sell to half of the bidders, and then Q is just chosen to make the size of the remaining learning groups proportional. Actually, maybe these two things should be swapped. Okay, I think it should be P is 1/3 and Q is 1/2, but it's not important. Then we give a bound on partition discrepancy in terms of learning theoretic parameters. And I've just condensed it in this theorem statement by saying, as long as the total welfare is sufficiently large with respect to the other problem parameters, then we can basically condense the partition discrepancy into contributing like a fraction, like an epsilon fraction of loss. Okay, but this guarantee still has this L term here. So what is that? So to analyze that, we need to like really think about specific auction classes. For example, like the class of lambda auctions that I talked about earlier. So yeah, we instantiate this for a specific auction class. It's a new auction class we introduced in the paper called bundling boosted auctions, which I won't go into what they are in the talk, but basically we are able to show that under certain conditions, selling to a P fraction bidders, you incur only roughly a P fraction loss. So yeah. So just quick situating this with respect to existing results. When bidders have sub-additive valuations, the best known approximation is a log squared M approximation. M is the number of items. When bidders have additive valuations, as far as I know, the best known is a log H over L approximation, where H and L are the highest and lowest values any bidder has for any bundle. So our guarantees require no assumptions on the valuation functions and are moreover fine-tuned to like structure in the set of bidders. And there are various scenarios in which conceivably our bounds could be a lot better. So just very brief overview of the techniques. So the partition discrepancy upper bound is in terms of the pseudo dimension, which is an analog of VC dimension for classes of real valued functions. And the proof basically leverages techniques from learning theory by drawing a connection between partition discrepancy and the L1 covering number of the class of revenue functions of this mechanism class. And finally, we introduced these population size independent auctions that are like lambda auctions, but can be parameterized in a way that does not depend on the number of bidders participating. And this in particular allows us to derive strong generalization guarantees that don't depend on the number of bidders in S at all. So the number of learning groups that the mechanism designer we need to draw, this actually has no dependence on the number of bidders in the entire group. Okay, so finally, in the last part of the talk, I'm going to talk about a similar but slightly different problem. And it deals with shrinking markets. So again, there's a fixed population of buyers, but the market is going to shrink. I'll formalize that in a second. And can we learn an auction that is sort of robust to a shrinking market? Shrinking markets are also prevalent. So some examples include cord cutters. So these are people who cancel cable TV subscriptions in order to move to like streaming services. The fuel market, so people moving from fuel to renewable energy sources. And labor markets among a shrinking population is another example. So how do we model a shrinking market? So again, we're in the same combinatorial auction setting. So there's a fixed set S of bidders and bidder valuations. And we assume that the seller actually knows S. So the seller knows the valuation of of the bidders in S. But what the seller doesn't know is what subset of S is actually going to come and participate in the market. So we assume that each bidder in S shows up independently with probability P. And in this case, what fraction of the revenue can the seller guarantee? Okay, so maybe at a first glance, you think the answer should be trivial. The answer should just be P. Or maybe it's even higher if you think revenue should have diminishing returns in the number of buyers. Here's a very simple example showing that that doesn't have to be the case. Just consider the VCG auction and consider an example where there's M items, and for each item, there's exactly 2 bidders who really like that item. One who values it at C, one who values it slightly less. Then VCG is going to sell each item to the person who values it at C, and that person is going to have to pay C minus epsilon over M for that item. So VCG actually does very well here, and it's going to extract revenue that's almost equal to the entire social welfare, so WFS minus epsilon. But if only a random P fraction shows up, a lot of revenue turns out to be lost. That's because, and the reason VCG does so well is because there's a lot of competition for each item. There's sufficient competition for each item. And if only a P fraction shows up, in order to get any revenue from this red car, both of these bidders ought to show up. Because if even one of them doesn't, VCG is going to sell the red car to the person who shows up for free, because there won't be any competition for that item. So hence the expected revenue that VCG guarantees is only a P squared fraction, but not a P fraction. So it turns out things can be much worse if you allow bidders to have allocational valuations. So far I've only talked about combinatorial valuations where each bidder can express how much they value each bundle of items, but you can generalize this to allow bidders to actually express how much they value each allocation. So I can express my preferences based on what items other people get. So this is even much more general class valuations. And in this case, it's pretty simple to come up with a scenario where the revenue you can guarantee by any auction is exponentially small in the number of items with respect to even the revenue of VCG on the whole set of buyers. And this can be seen by taking the previous example, but sort of augmenting the set of items and bidders such that so we have now a bunch of sort of weak bidders who all have values that are very small. And okay, and we'll add enough items for the weak bidders as well. And we're going to just modify the valuations of these guys, the strong bidders, so that the valuations are pretty much the same as before, but they are the same as before only if each weak bidder also receives at least one item. And otherwise, the strong bidders are also going to have like 0 value for the item. So the strong bidders really want weak bidders to also do well in this auction. And in that case, for any significant fraction of the revenue to be generated, all weak bidders must show up to participate in the market. And that happens with probability p to the power of the number of weak bidders. And so we just computing this out, you show that this is pretty much the maximum revenue you can generate, you can guarantee in this case. So this is a case where if a p fraction shows up, the expected revenue is exceedingly grows exponentially small the number of items. Okay, so the first result here is how much revenue can actually be preserved. So we need some condition that precludes bad examples like the one I just talked about. And this condition is going to be something we call winner monotonicity. And it's this natural condition. So if we want the set of bidders and their valuations to satisfy the property that if bidder I won in the VCG auction and bidder J left, then bidder I should still win in the VCG auction without bidder J. So the previous example wouldn't satisfy this property because if like weak bidders left, that would affect who won in the auction. So in this case, we showed that there's a lambda auction. And again, so I know it's been a while since I talked about lambda auctions, but the details of what they are don't matter here. It's just a large family of VCG-like auctions that allow for a lot of freedom in the mechanism design. So we showed that there exists a lambda auction that guarantees this fraction of revenue. So there's a p squared term here. K here can roughly be interpreted as the maximum number of winners who can ever win in VCG. And gamma is just a constant that depends on the set of bidders and their valuations. And if this bound looks complicated, a more maybe like an easier way of interpreting this is like maybe a corollary of this bound that we get. So we get families of bounds when the mechanism designer places practically motivated constraints on the auction setting. And an important one is, suppose the seller limits the number of winners. So the seller just says like, okay, even if I have 100 items, like I don't want to be selling to 100 different people. I only ever want 5 people to win in my auctions. Then the parameterized nature of this guarantee is going to give us a guarantee where K is roughly replaced by 5. And welfare of S is replaced by the maximum welfare under this constraint that 5 people can ever win. Another setting in which we can get like another parameterized sort of family of guarantees is when there are bundling constraints to the items. So for example, if the seller stipulates that certain items ought to be sold together, then we can refine this guarantee to take those constraints into account. So I'll give a very high level proof sketch. So one important thing is basically that the class of all lambda auctions is super, super rich. So you can show pretty easily that for every subset S naught, there exists some lambda auction that would extract revenue equal to the welfare of S naught. Of course, applying that lambda auction is not truthful, but it's just saying that, if you didn't care about truthfulness in the complete information setting, given any set of buyer valuations, there exists a lambda auction with parameters that depend on those valuations that would extract the maximum possible revenue. And here's like one silly observation. Well, okay, so there's 2 to the n possible subsets of people that can show up. So like let's choose one of these lambda auctions at random, and that would roughly give like a 1/2 to the n approximation. Okay, I mean that's a terrible bound, but yeah. But that's there. Okay, so let's try to just use that logic to cut down on the number of subsets we ever need to consider. So we define an equivalence relation on subsets of bidders, where 2 subsets we'll say are equivalent if the corresponding lambda auctions given by this line here, so I said for every subset there exists a lambda auction. It turns out for a lot of these subsets, that lambda auction is going to be the same. So we define an equivalence relation on subsets, where two subsets are equal or equivalent if the corresponding lambda auctions are the same. So the first thing we show is that with constant probability, the welfare of this random p fraction of bidders that shows up is not too small. We'll call such subsets heavy. Then the winner monotonicity property is going to allow us to bound the number of heavy equivalence classes. And when I say heavy equivalence class, I mean, for each equivalence class, there's sort of a unique way. We show there's a unique way to choose a representative subset for that equivalence class. And we'll show that the number of such equivalence classes with a heavy representative subset cannot be too large. And to do this, we exploit some sort of combinatorial structure on the subsets that winner monotonicity imposes. In particular, you can arrange these equivalence classes in a tree, and winner monotonicity is going to show that winner monotonicity combined with only considering heavy subsets is going to allow us to truncate the tree pretty quickly and only consider a relatively small number of subsets. And then we can, once we've cut the number of equivalence classes that we need to consider way down, then we can use the thing that previously gave us this kind of silly approximation to say, well, if you now chose a random lambda auction, it would give you an approximation that was just equal to the number of heavy classes. So then there must be a lambda auction that achieves that approximation and expectation. Right. Okay, so far I've just told that there exists a lambda auction that achieves this guarantee. How do you actually choose an auction? I mean, if you go and investigate the proof, the proof itself can be made constructive, but that's gonna, first of all, only yield this guarantee, which, I don't know if this is even close to optimal. It's just, one positive result for this problem that people haven't really studied at all. And, as we showed, can be the revenue loss in certain cases can be really bad. But instead of doing that, the more natural thing is to learn from samples. So the seller knows P, and the seller knows the set of bidders beforehand. So the seller can draw samples himself and do empirical revenue maximization before the actual subset of bidders who's going to participate actually shows up and reports their valuations. So unfortunately, lambda auctions, the class of lambda auctions is so rich that doing this would require exponentially many samples and number of items to learn a good lambda auction. So in the paper, we look at a slightly restricted class of lambda auctions called gamma boosted lambda auctions that are restricted to give positive boosts only to allocations in this set of allocations. And in that case, you can get similar guarantees for this class, and then you can get algorithms to do learning that have runtime that's exponential, but only in this number of allocations and polynomial and all the other parameters. I guess the only caveat there is that you need to leverage routines for solving winner determination, which is a generalization of the problem of computing welfare maximizing allocations. So that's known to be NP hard, but there's various work. There's a lot of work showing that it can actually be done practically, efficiently in practice. And for example, there are classes of valuation functions for which doing that can be done in polynomial time. Yeah. Okay. So yeah. So that's all I have. Thanks everyone for listening, and I'm happy to take any questions if there are any.
I have a question. Thanks for the talk.
Yeah.
Yeah. So throughout this, you consider there's a single seller, right? So is there I don't know, is there an extension you can think of where there are multiple sellers and either a single buyer or?
Yeah, that's an interesting question. So there are these things called procurement auctions where there's it's sort of like what you're saying, where there's multiple sellers and sort of a single buyer. So you could think of a case where maybe there's like a construction company that wants like a bridge to be built and is auctioning off the task of building the bridge to multiple sellers. So like, right, because in that case, like the sellers are the ones that are going to need to like get money to do the project. And yeah, I'm not really sure.
Yeah,
I don't have like,
I just thought of it as maybe an alternative assumption in your last bit, because when there are maybe a small number of sellers, even if fewer buyers are showing up, they might be forced to buy from one of these sellers. So that might give a better lower bound on the revenue in a sense. Yeah, I don't know if it makes sense.
So you mean in this like shrinking market setting?
Yeah.
I guess I'd have to think a bit more about that. So I know like people think about sort of reducing supply in order to like spur competition between buyers to increase revenue and things like that. So maybe something along those lines, like your suggestion could work along something along those lines. Yeah.
Thanks.